Hello, everybody. Thank you, John, for the introduction, and Adam. I'll stop my video to have a better link. Can you see my screen? I hope so. My name is Israel Koffman. I'm from a RunEL company, which is a startup in Israel dealing with 5G infrastructure. And the purpose of this presentation is to describe the radio access network of the 5G link that we implemented at IoRL at two different bands, the millimeter waves, and for the first time ever in 5G light over visible light. So it's a very innovative concept that was provided in this project. But before we go to the IoRL, let's look at the at what is the 5G network. It's a concept. So usually the 5G networks are, as any other cellular network, consist of the core network that John already described a little bit, where you have the applications and the management and the services, and those are connected to the user terminals that you can see them here. Let me put it. You can see the user terminals or devices in 5G can be not only cellular phones, but any type of devices and dresses and everything, and glasses. And what connects between the core network and the user terminals is the RAN. Usually it's called the base stations. And the purpose of this presentation is describe how we implemented this RAN in IoRL. So usually the RAN can be implemented as a one unit or can be implemented in a distributed architecture. And according to the 3GPP standard, there are different types of distributed RAN. Usually it is done in three different units: the send control unit, which includes the layer 3, the distributed unit that includes usually the Hi-Fi and the layer 2 or the MAC, and the radio units, which include the low power portion of layer 1. So we decided at IoRL to implement the distributed architecture. And we use these three types of units, the CU, the DU, and RU. We just call them in different names. We call the DU the DRAN. We have a computer or the intelligent access network in the project, and we have the RU, which is the remote radio heads. And in this slide, you can see how we implemented it in a different way. So we have the core units, and we have two boxes that are outdoor units, or you can put also indoor. The DRAN that include the Hi-Fi layer, and the RRH or remote radio light head, where we put the low-fi layer. And also we have the central units that were close to the core network. And then we connected via, we have two links, one at b.VLC and the other one in millimeter waves from a single remote radio head. Here you can see in this slide the complete network. I will not go into every one of the modules, but here you have the radio access network in the center. In the right side is the core network with the applications and the services, and the left side are the user terminal. And here you can see the layer 3 and 2 were implemented on the computer. Okay, here this is a computer. Then we have the DRAN or the DU that was implemented on a FPGA. And also you have the remote radio light head that were implemented also in FPGA mode with baseband radio units that drives the two type of frequency bands. One is the VLC, visible light communication, and the other one in millimeter waves. So we can connect user terminals in two bands from one remote radio control head. And this is how this slide describes how we implemented these functions internally or from the hardware point of view. Here you can see that the MAC layer, the layer 2 and also layer 2 were implemented on a regular computer, x86 or a server. Then we have the DRAM that was implemented, the Hi-Fi and with GPS synchronization and all the Ethernet links were implemented on FPGA-based network. This DRAM connected, was able to connect different remote radio head controllers via an Ethernet ring, which is also a new concept in this for 5G. And in the remote radio lighted controller, we have also an FPGA card with the low-fi, and we have an RF card that drives the IF bandwidth to the VLC and to the millimeter wave. To the millimeter wave, the baseband was around 3.5 gigahertz, the IF frequency, and then in VLC, it was a lower, almost DC IF signal. So this is how it was implemented from the hardware point of view. And here you can see also the concept itself. Those are the different modules for the intelligent home radio network with layer 2. Then we go to the DRAM with the Hi-Fi layer, and then we have a ring that can connect actually up to, as John said before, 32 different remote radio light heads to cover a full house or a station. And each remote radio light controller has two drivers, one for the VLC and one there for the millimeter wave. So this is how this network looks. And it is, of course, scalable in order to provide full coverage to whatever you like to cover. If we look internally into the DRAM, the main modules that were implemented on the DRAM, here you can see on the slide, I'm not sure you can read them, but it's written as well. So the main modules in the DRAM, in the Hi-Fi, were the error correction modules, which were the LDPC in the for the data, and the polar error correction mode for the control plane. So both of these error correction modules were implemented in the DRAM, and they work perfectly. If you look at the RH, or the remote radio light head controller, also was implemented on FPGA. You can see the board here on the bottom left side, and we have an RF module inside the remote radio light head that drives the millimeter wave modules and the VLC modules with IF signal that are pre-configured. And in this module, the main functions are described in this slide. So we have the modulation and demodulation modules. We have the PRACH process, the pre-coding, the mapping, the IFFT and the FFT, the cyclic prefix extension, also the low IF generation for VLC, and the 3.5 gigahertz RF modulated signal for the millimeter wave interface. So all these software modules were implemented on FPGA, the RF module via RTL type of programming. In this slide, we describe the connection between the remote radio light head controller to the actual millimeter wave and VLC modules. It was a rather complex type of interfaces because we use different IF for the VLC and the millimeter wave. We have TX channels, RX channels. We have different polarizations for the millimeter wave. So I will not go in details, but you can see it was a rather complex connection that we implemented, and it was a collaboration between different companies like RunEL, Tsinghua University, and Fraunhofer Institute in Germany, and Tsinghua University in Beijing. So it was a long an integration process. Of course, were helped by the University of Brunel and Leicester. So these complex interfaces were implemented and operated. Here you can see the hardware and the pictures of how the test sites. Here you can see the PC with the layer 2 and layer 3. Here, this is the DRAM unit with the Hi-Fi, and this is the RRH unit with the Lo-Fi and the RF module that drives the VLC and millimeter wave module that actually they were installed in these light heads on the ceiling. And here you can see the measurement equipment and the power supplies that were driving all these light elements here. So, and in the next picture, you can see the actual setup. In further presentation, we will go deeper on the explaining all the setups, the applications, and the services and the measurements. I'm just showing the picture itself, how it was installed. So you can see the 4K TV here, the layer 1 and layer 2 processors here, and the millimeter wave RX here, and the VLC RX here. So all this picture, how this all modes were implemented and tested, and of course you can see the light here on the ceiling. So I'll try to start summarizing the RUN main features. So the main feature of the RUN were dual connectivity, when one a remote radio lighted for VLC millimeter wave to have it over the air. The remote radio lighthead were based on a chip developed by RunEL with ARM cores and FPGA. It was provided by Xilinx. The remote radio lighthead could do 4 beams for IoRL, single beam allocated for VLC and another one for millimeter wave. To extend the coverage area, we use VLC lamps, up to 8 VLC lamps, and remote radio lighthead analog output. And for the downlink and uplink interface for the millimeter wave, we use 3.5 gigahertz band with RF splitters. The bandwidth for the VLC was 10 megahertz, and we try to extend it to 20 megahertz. For millimeter wave, we use 100 megahertz bandwidth. The Ethernet ring, the data rates was 10 gigabit per second. We have several of these Ethernet rings, up to 8 rings like that can be used. We reach 20 megabit per second throughput and 20 megabit per second, 100 megahertz bandwidth. It is a full duplex FDD and TDD solution, so it can be used in any type of these allocations. About the key performance achievement, already John goes through this slide, so I will not cover them now, as well as this slide that John already covered them. just I want to mention what, to my opinion, were the most the great innovations in this in the run portion of this project. The first one is the distributed architecture with the physical layer split. We already done it when we started the project in 2017, and now lately this become the mainstream of the 5G implementation with the O-RAN society introduced the O-RAN interface that is a physical layer split and the 7.2 option. But IoRL came first. And I think another great achievement of IoRL is that we were the first ever to do a 5G link over VLC spectrum. I think we were pioneers in this area as well. And this, of course, needs further research, but we put the first stones in this area. This is the acknowledgement for the European Union that funded this project. And with this, I complete my presentation. Thank you very much for listening. If you have any questions, I will be happy to answer. And you have my email here also. You can write me or via the chat. Thank you very much. And I pass it back to Adam to introduce the next speaker.
Yeah, thank you very much, Israel, for your talk, and thank you for keeping to the time. I still don't see any questions in the chat channel, but maybe we have time for one quick question if there is anybody who wants to ask a question. Let's experiment with this aspect just for a moment. So, is there any question to Israel right now? Or if not now, then we can try to come back to issues later. Yeah, there is one. Yeah, why are you using 3.5 gigahertz band for millimeter wave instead of 24 gigahertz or 60? That was a question that just came in on the.
The output of the design of this radio, the RF portion was for the sub-6 frequencies. So we use the 3.5 gigahertz to up convert it to 40 or 60 gigahertz that was used in the millimeter wave. Those were the radio units. Millimeter wave radio units available at Fraunhofer that will be described in the next talk. So the reason was that was the IF frequency that we choose to up convert it to the millimeter wave.
Yeah, I'm not sure. Did you pass me the presenter role actually already, or the best would be if you can pass it to Robert directly, or maybe can I ask help from Xun to help with this passing on the presenter role to Robert. Robert Muller is our next speaker. He's from Fraunhofer IIS.
Sorry, I think another question he asked here for.
Was there? Okay, let's check. Yes, okay. Oh yes, I mean the some of the answers to. Okay. So there is one question. When do you expect this technology to appear on the market as a product? Well, I think maybe I should pass it back just for a moment, not the presenter role, just the answer to Israel. Maybe you want to comment on that. I mean, you went a long way in developing your technology and integrating it. I mean, Israel, do you think it's getting near to being ready for the market, or
I believe the millimeter wave is. I think 5G over millimeter wave is already in the market.
Yes, but I'm talking about your own one, right? Let's put it that way, right? I mean, with the explicit support to very low latency and so on and so forth. So,
our RunEL products, the DU and the remote radio lighters are already ready for the market. they are still on FPGA mode, but for this stage in the market, we believe it's good enough. In the future, we may need to convert the remote radio lighthead portion from an FPGA solution to an ASIC solution to reduce the price level, because we believe that it will be a very common product. But for this time, the initial market, we believe that we have a commercial product right now.
I'd like to add 2 points as well, Adam, if you don't mind. The first point is in response to the first question about 40 gigahertz and 60 gigahertz solution. The 60 gigahertz solution we found was very expensive and couldn't be replicated because of supplier problems from the US suppliers. And the second answer was the RunEL solution, this distributed RAN solution, was also used in other projects, notably in the 5 Genesis project.
Thanks, John. Exactly. This was one aspect I also wanted to chip in, that it needs to be understood that this solution, as it is now, or as we present it here, we picked it and we used it because it was particularly suitable for research projects such as the IoRL. But I would like to also emphasize, just John said, that it is already being used in other research projects, notably the 5 Genesis project. And I think also, I believe in some other upcoming project, it will be used as well. So it is making its way on the market. With the FPGA implementation, it's particularly suitable for research projects such as the IoRL. But eventually it will make the transition on ASICs and can become kind of a mass market product as such as well. But yes, there are millimeter wave products already on the market. And with that, I would like to really now pass on to Robert, not to lose completely the time aspect. So Robert Muller is our next speaker. He's from Fraunhofer IIS, Integrated Circuits, and he will present us the millimeter wave modules and antennas of the project. Robert, please.
Hello, everyone. Hello, Adam. I hope I share the white screen. This is a full screen for the presentation because I have 2 monitors.
Yes, yes.
It's not like the previous. Okay, this is well. Hello, welcome everybody. My name is Robert Muller. I'd like to give a short interview to the millimeter wave modules and to the antennas. I'd like to say something to the 60 gigahertz questions. I think we have tested some demos with the 60 gigahertz modules, but they was much bigger than the final version what we developed for the radio lighthead. And the 60 gigahertz has the main problem is that we have a distributed board, RF board, and antennas on the outside of the lamps, and we need some cables from the boards to the antennas. And at 60 gigahertz, we have much more attenuation and losses go from the up and down converter to the antennas in a good position of the lamp. But this was one reason, and was also the cost for the components and the manufacturing cost, that the 60 gigahertz was in this stage or at this time very unusable for a cheap millimeter wave platform. And this project was more related to 5G, so 60 gigahertz is not really 5G. 60 gigahertz is more or less related to I2B to Wi-Fi. It's a ESM band. So that's what is a couple of reasons why we changed to the 5G bands, to the millimeter wave bands of 5G. Okay, so then next I'd like to focus more on my talk to the millimeter wave modules. So we start with, again, the overview of my talk. I start with a short overview about the architecture of our system, what we planned at the beginning of the project for the millimeter wave. Then I say something to the requirements to the millimeter wave design, what I already mentioned. Then I say something to the challenges, what is now the challenges on millimeter wave system design. We developed 2 different converters. We developed one ultra wideband converter, it's meaning for very broadband baseband signals, and we developed one multi-channel transceiver, what is more related to this idea of have a lot of access points in a room or in an area or in demo sites to have a good localization services and other things. And also we developed some millimeter wave 5G broadband millimeter antennas, and all the things is here low cost, also at least I like to go to the old low-cost ultra wideband two-pole antenna, what we like to include in the final version of our demo set. So the previous idea was that we can change every lamp in a museums or another scenarios to like a radio head that have a millimeter wave and optical. The idea is to combine both technologies to increase the localization service and also the data rates. But for data rates, a millimeter wave is mostly enough, but the light give you a good quality for the localization services. And this was one main focus in this project. The first idea was to have a very small board, including the LED, also the light and the millimeter wave modules. In a final demonstration, we doesn't have it yet because the integration on one PCP is very, very challenging. But we have one compact millimeter wave converter. We have one solution for the b.VLC. And also for the user terminal, we're thinking the first time that we have a small model what we can use, for example, in a USB 3C and a user equipment to connect it very easy to show. Also, this equipment is in a demonstrator a little bit bigger since in the previous planning. But this was a system idea to have like a compact system, have a light and millimeter wave together, have a broadband signal, and have a good quality in localization and data services, and open new applications or a new quality in applications like localization and also applications for the museum, for the industry, and also another sites what John already presented. Okay, now we focus a little bit more to the millimeter wave equipment. What is the requirements for our millimeter wave? That is our goal was we like to cover the full 5G millimeter wave frequency bands with the millimeter wave. This is going in a world around from 24 to 40 gigahertz, now to 43. It's a little bit increasing in frequency. The goal was a minimum 1 gigahertz of IF bandwidth that we can have like a good localization services with broadband signals. We like to have a compatibility for all baseband units, what is from the different partners in the IoRL project available, for example, for the RunEL baseband unit or also from Viavi. Also, system clock is now for the current system is at 10 megahertz, so that we have a good current clock synchronization. We like to have a multi-channel support for every radio LED head. It's meaning we like a dual pole antenna at the access point a minimum, because we like in every time a signal to the UE without to check the rotation or to have some problems with the polarization. This is a problem sometimes in millimeter wave. Yes, we can use circular antennas, but with polarization, we have also the possibility to make polarization multiplex that we can increase the data rates in the least. And another very important point on the system design was a low-cost aspect. So we are limited in the cost in this for the material cost, because we like to build up a system what is useful in higher numbers of amount that we have, like in one museum or something, 40, 50 in at least, or more access points. And then it's the reason that we build up with like a standard components, with already housed components, 40 to 60 gigahertz systems. We need to pay a couple of €1,000 for one up and down converter. And here was the idea to build up a cheap multi-channel up and down converter to provide a compact system for the lamps that provides a full up and down mixing for the baseband signal, and what I already say, small dimensions. So what was the challenges for this one? The biggest challenge for us is currently now to get the chips for the millimeter wave range, and they are mostly expensive. It's a big run on the 5G millimeter wave bands. There's a lot of chips now available in principle by different suppliers, which depends how many amount you order. It's difficult to get something in short time or not, but in principle, the mixers, the power amplifiers, and all the stuff in a small number of samples is very expensive. The next problem is to get millimeter wave antennas for the full band. It's like also very expensive when you buy a horn antenna or something else from F-Spin or another companies like Coupa or something else. Horn antennas for the full 5G band, what covers all frequency, you need to pay a couple of €1,000 for one antenna. And mostly the horn antennas are too big for our implementation in the demonstrator. We need more than 10 modules for the access point and user equipment. So that was like the minimum numbers what we like to include it in our demo set. And our estimated price per module was in the first time €1,000 per module. including the antennas. This is a very challenging price. I can say it doesn't fit this challenge because all the components what we include in the modules for one transceiver, it's more than 1,000 euro currently. So, but I will say later on how much is the overall cost, including the manufacturing and the housing. But this was in a previous stage our goal for one TX or for one access point, including transmitter and receiver. Coming to the ultra-wideband converters, here's a first version of our ultra-wideband converters. It's a very simple setup. It's only mixers, some filters, and power amplifiers. In principle, there's some filters more included. This is like built up with primarily analog devices components on a LTCC substrate. Here was the idea to have a big IF bandwidth to cover the full, also the full frequency range of 5G. We have on this version around 20 dBm output power. We have a gain control on the receiver side inside, an up and a down converter. We have like a LO range here from 12 to 20 gigahertz, so that we need the external synthesizer. This is like a little bit more complicated for this version to get the white clock for the up and down converters. And every module is like produced at the dual channel system. This meaning we have 2 TX channels or 2 X channels that we have always dual pull support for the up and down converters. The next picture, or the next slide, we can see the final version after the production. We produced this on 9K7. This is like a special low temperature co-fired ceramics. It's built up for high frequency support. Here we can see the final version of this up and down converter. It works okay, I will say. The most problem is here that I have a big bandwidth of 10 gigahertz I have, and we have only in the first demonstrator low bandwidth. So we need to include some filters. And the second thing is this module is very expensive because the problem here is like the IF connectors and chips cost, and the production for this module is like more than 4,000 euro per module. This doesn't meet our idea of cheap up and down converters for our IoRL project. But for testing and for demo set, it works very well, and it's like a compact version with 5 by 3 centimeter around. Yeah, next one is like our multi-channel final version transceivers. This is more like a compact system included. Here we use some new chips from also analog devices, the ADMV 1013 and 1040. This is already a system on chip up and down converter, which include a lot of functionality. We include this one of like a PCB or a layout. We include also a synthesizer that what makes possible to use the 10 megahertz system reference clock of our IOL demonstrator and supply this to every current to every channel. We include some additional LNAs in this version, and this version have enough power to cover distances up to 150 meters with a SNR of 20 dB. So it's enough for our scenarios, also including a couple of reflections. We use for this one also, a special high frequency material, also that we have like a good RF characteristics, and include also a small Android Nano for controlling all the stuff. And also in the end, we get a compact module that have a dimension of around 10 by 10 centimeters. Okay, I see here, quite near. And this is really compact. It works now well. It's finished, and we have the first test done and will be included in the final demonstrator. Yeah, and the maximum output power for this version is around 10 dBm. Here we can see the final layout from the production. Now was in the manufacture, also in the assembling process. And now it's like in the lab in Erlangen for the test and programming for the final steps. And this will be the final version for our project. I think this is a good compromise in price. It costs around what I read already 2,000 euro in the previous slide. The most expensive parts of this one is the RF chips and the connectors for the SMP connectors. This one altogether costs around 1,500 euro. That is the most expensive stuff for this, how can say, design. The manufacturing and the PCB is the rest, and the housing, and this is more or less the less part of this millimeter wave system. Okay, next we have also the problem, we need antennas. We have a big range, and everybody he buys some millimeter wave broadband antennas, he knows that the antennas are very expensive on the market. So we think about how we can get some cheap antennas, because we need 10 antennas or more when we have dual pole, or a couple of antennas for the demo set, and then we need the broadband antenna. So here's a very cheap version of a thin horn antenna, manufactured in Rogers, and it's sold it itself in a lab. The most expensive stuff on this antenna version, what you can see on the right side, is a connector. His is, I think, make 80% of the cost of the antenna. And another one is very simple. It's easy to manufacture. Covers the full bandwidth from quite near 18 gigahertz to 40. Have some ripples, but it's better than 10 dB for the full band. The gain have a little bit variation. It's not so perfect that we imagine, but for the hand manufacturing in the lab and for easy manufacturing, I think it's a good antenna. The antenna have an opening angle of around 60 degrees. The gain is 80 dB, and the antenna is really compact. And what I'll always say is it works up to around 50 gigahertz, and all the costs, including the manufacturing, is less than 40 euro per one antenna. We developed also another antenna for the system. It's like a very compact dual pole antenna, what you can see here. The optimum working range for this antenna type, it's around from 36 to 40. It works, you can see in the diagram, also in the lower frequency band, not so well in one polarization. This is here the problem. We direct the coaxial cable to the PCP. This makes the antenna much cheaper and makes also more compact. The problem is, what I already say, is that the millimeter wave up and down converter is separated from the antenna couple of centimeters. So we need some cables to bring the signal outside of the radio light head. And this is the most expensive stuff on the antenna, is like the millimeter wave cables and the connectors. We can also increase the bandwidth of this small antenna when we're using SMP connectors, mini SMP connectors to the full band, but the connectors and the cables, including the adapter cables, is so expensive that is for the demo set, and we're using only the higher frequency band, is not useful. But we can extend the frequency of this small antenna every time. This antenna have also a gain of around 8 dB. Its dual pole have also 6 dB opening, 3 dB opening angle of the beam pattern. It's very well to provide a full signal to the full different room scenarios in our IoRL project. And yeah, we make the producing is now we use some special metal printing printers, and then bring it to the metal. To the Hello. Sorry.
Yes, you are still connected.
It works again, or I have some disconnected. Hello?
No, you are not disconnected. I hear some background noise, so I ask everybody else to mute.
You're okay. You're okay, Robert, to continue.
Okay. It's in any case, I think it's the last slide. I'm really fast now. This is a final antenna for our demo set. The overall cost is here a little bit higher because of the cables what we need to connect for the antennas to the millimeter wave up and down converters. This costs around 100 euros. This is the most expensive stuff. Yeah, and that is like the final demo set. Then we use up and down converters, the system, the full system, and also this compact antennas connected to the RunEL or the Viavi baseband units for the millimeter wave part, and then we have a good coverage of the room. The output power from the test is enough to cover the full room, and this is also now another version of the millimeter wave converter in the production with an additional power amplifier, so that we have a bigger coverage for different scenarios. I will say thank you for the attention. I give you also a thank you to the European nation to found this project. I think from our part, we have developed a nice compact up and down converters with different technologies. Now we doesn't match completely our goal to get a very cheap up and down converter. That depends there that we use a broadband. We like to have a broadband signal, and also because we doesn't match requirements of low cost, is like we have dual pole compatibility of the modules. So this both things makes the modules a little bit more expensive since we imagine in the beginning, but in the end it's like a nice things to include in the lamp, and in the end compared to other things what you buy now commercial on the market is, I think, is a good compromise for for the first demo set for our IoRL project and also for future project, they like to deal with 5G millimeter wave frequencies. So I'd like to thank you for the attention, and if you have any questions, you are welcome to ask me. Thank you.
Thank you, Robert. Thank you for this interesting talk, and also thank you for keeping to the time. There has been lots of exchanges of information on the chat channel, so I also would like to flag it to others, but I haven't seen any particular question to your presentation. They were more focused on still on the 5G RAN realization by RunEL. I mean, unless we have one question right away to Robert, then maybe we will move on to the next talk about visible light communication, and the speaker will be Zhang from ISEP. I mean, if there is any question to Robert, we can come back to it a bit later, or we can try to address it in the chat channel. Yeah, Shun, can you take over maybe?
Yeah, I think it's Ben. Ben will make the presentation.
Oh, sorry. Okay,
Yeah, it's okay.
That's my mistake. Okay.
It's afternoon.
Yeah, correct.
Would you like me to share now?
Yes, please. Yeah, sure.
No problem.
So the next speaker is actually Ben Meunier. He's from University of Brunel, and he will present the visible light communication aspects from the transmitter side.
Can I just ask that everyone sees the presentation clearly?
Yeah, we can see it. Yeah.
Sorry, I didn't hear that.
Yes, we can, Ben.
Perfect. Brilliant. Thank you.
Sorry, Ben, just take care of your configuration of the screen, because we can see the presenter version.
Oh, right. Very sorry. That'll be an issue on my part. There we go. Okay. Yeah, so I'll be introducing the Internet Radio Remote Radio Lightheads system. And so throughout this presentation, we're going to be going on a journey through the hardware requirements, the scenarios of the IoRL project and the specifications within that, the design roadmap that we used for designing the radio lightheads, the final design of the ceiling light, which we implemented at our test facility, and the manufacturing process for that, and then finally the actual testing of the radio lightheads in Europe. So here you can see the initial hardware requirements set up by the project a few years back, where we have the power driver providing supply power to the VLC board that you can see here on the right, as well as a millimeter wave module, both of which have their relative antennas. We were using patch antennas for the millimeter wave and LEDs for the VLC signal. We had to fit all of these form factors within various radio lightheads, and that's what I'm going to be talking about today. So firstly, the Internet of Radio Light project has various scenarios that we're obviously using: the supermarket and train station, museum, and the home. For the supermarket and train station, we decided that we would try and use a similar design to the lights that are already there, the implemented ceiling strip lights. And so we designed a strip light accessory to be an add-on to those and provide signal and hold the components presented in the previous slide. In the museum, they were very adamant to use spotlight systems. So we designed spotlights for them. This was to maintain a dark atmosphere in the museum. And within the home, we decided to use ceiling lights or pendant and pendant strip lights. And we'll be talking further about these kind of designs throughout. So with these, we initially considered trying to take existing systems, manufactured systems, and trying to embed the hardware of the IoRL project within them. We decided in the end to actually opt for creating our own radio lightheads because this was a lot easier to fit all of the large components within that. And we could then design the radio lightheads to perform the best for the project. So initially, our ceiling light design, as you can see here in the first image, we had a very, very large LED light array to provide general ambient light around the room. However, the VLC driver, which was needed to power the VLC components, was not powerful enough to kind of illuminate all of these LEDs, and the positioning array was too large. This array was too big to get a precise position from. Therefore, we opted for solution 1, which was to add a small patch of LEDs that were designated simply for the VLC transmission. All the rest would be for general illumination of the room. However, the general illumination LEDs were behind a diffuser, so they weren't so harsh, and this blocked the VLC signal. Therefore, as you can see, option 2, we separated the VLC signal, put that in a central and raised location so that the VLC transmission was separate to the actual ambient light. Finally, we noticed that the LEDs themselves under performance tests did not perform too well, and so we opted to use a COB chip on board light, which was more powerful for this use. Finally, here you can see the transmitter chip on board light performance. Luminosity showed very good results, 130 lumen per watt. The thermal simulation, which was quite important to make sure that we didn't overheat any of the components within the radio light heads, was also very low, and so that was satisfactory. And here you can see some of the performance results for that COB light. Because of this, we decided that the ceiling light would have a separate driver to power its large LED panel, which would be completely isolated on its own. And all of the light systems that we would design hereafter would contain the COB light as well. This would mean that we would have uniform VLC transmission should you choose to use different lights within the house or building. The spotlight itself, so the second light that we used, was to be implemented in the museum scenario. And the challenge was the fact that the museum scenario had existing rail systems for their power distribution. And so we had to house the hardware in a system that would attach onto the rail, connect the power via that rail, and then would also look like a decent radio light head spotlight. The approach was to initially, as I said, take a light from our Shanghai Philo Yamen collection, which are the manufacturers we were working with. And then we decided to keep the electronics and joinery parts, so these connections and the main light, while redesigning the housing, this large area around them, that would house most of the large millimeter wave and VLC components. The introduction of the COB for communication, so the chip on board light that we've just tested, meant that we had to enlarge the actual light housing, and for strength, we changed some of the materials around the housing to aluminium. The pendant light, we designed this for the house scenario, and we decided that it would be best that we create a light rose or a ceiling mount that would contain all of the hardware, and then any extension we wanted to put could be connected for the VLC. So this would be adaptable for various light shades, light strips, and so it was a little bit more modifiable, which is obviously nicer for various designs. The approach, we housed only the IoRL hardware essentially in the main lighting system, and there was no internal light source. The light source was down here below. And here you can see an exploded view of the millimeter wave box, VLC antenna, and the housing top and the patch antennas as well. The accessory lights, we designed this as a backup plan for consideration when the lights could not be changed in a scenario. And it basically houses all of the IoRL project components. We designed 2 of these, one without LEDs, so this would be connected to an existing LED source and would be powered via the VLC driver, similar to the pendant design we just saw, and one with LEDs on the top, such as a COB light source, so that it could be an all-in-one IoRL system that you could just implement anywhere you like. Because of the transition of the entire collection to the COB light source, we scrapped the without LED scenario because they all had to implement the COB light. The final design of the ceiling light itself used ABS plastic for the actual outside casing, which we know to perform well for impact resistance. It obviously has low temperature resistance as well, and it provided a good finish and result. We did want to change the outside casing because we suffered small cracks on the sides, And so this is under review at the moment. Here you can see all the components, the VLC driver, which we can use to dim or brighten the LED panel here. The LED panel, of course, covered in LEDs for the general illumination. And then finally, the actual VLC COB light on the top, which transmits the VLC signal independently. And then finally, we had various testing within Europe. So here you can see the actual radio lights implemented on the ceiling. So we had 4 here used, and we were using those for all of our testing, which we mounted to wooden brackets on top of our aluminium frame. Finally, here is us performing some testing of position by using transmission and measuring the center angles. Here's the VLC receiver. So this is us testing the actual signal from our transmitter radio light heads. That is my presentation. Thank you very much for listening. Do you have any questions?
Thank you very much, Ben, for your interesting talk. Yes, there was one a question where, you know, one of our attendees commented on that it is really interesting to combine the illumination LED lights with the communication. Can you comment on maybe on the power consumption of such a combined solution?
I don't have the exact scenarios. I don't have the exact measurements or data to kind of comment on that accurately now. But we found that actually it was quite a challenge because as we saw, our initial kind of target was to implement all of the lights, just take any standard light system, implement our VLC driver, and it should perform. However, in reality, the VLC driver was limited itself. All types of different light systems perform differently because of their strength, their intensity, their warmness. And so there's various factors you have to take into account. And this is why we decided that we would, you know, test one best performing light system and then implement that all round throughout the radio light heads. Not only because we knew that it performed well, but because we wanted the signal to be uniform. So in a, you know, in a common user scenario, you wouldn't have one light system everywhere. And so we wanted to make sure that the VLC signal, especially for positioning, always had the same strength so that we could perform the positioning algorithms correctly.
And you did compile a power budget for the whole system for
yes, there was
Sarah Verobia was asking for it, wasn't she?
There was an overall power consumption of the radio light heads, as well as most of the RAN as well.
And the other thing we found was that we couldn't just use a normal electrical cable for providing the VLC signal to the lamps because of it acted as a type of antenna. And
that's right. Yeah. We had to modify because the VLC driver was obviously SMA connector for coaxial cables. We had to adapt the transmission for the lights. So they usually use just a simple, you know, copper cable for positive and negative live and ground. And we had to adapt that so that it could actually feed in the coaxial cable. And because of this, we suffered some attenuation from that small amount of copper cable that was still left. So this is something that would probably be needed to work on using, you know, specially designed lights with special connectors.
Thank you very much, Ben.
Yeah, another question I see.
Oh, is there?
Why did you consider having so many small LEDs for illumination? Right, so
that was part of the design, wasn't it, Ben?
Domenico. Yeah, so initially this was a manufacturing standpoint. They designed the light to have the luminescence that they expected. So they decided how many LEDs we put on it. I agree that we could have reduced the number of LEDs, which would obviously reduce the amount of noise that you're going to expect in a system. And with the other light systems, the ceiling light was the only one where we had a kind of a separate designated panel. All of the rest, the spotlight, the pendant, were designed so that the VLC source would be the main light source, or the only light source, sorry.
Thanks a lot once again, Ben. I was just posting it on the chat channel that for the sake of giving enough time for the other speakers,
of course.
we need to move on.
Thank you.
Any further question to Ben and regarding the visible light systems, please post it on the chat channel. We will do our best to answer you. And yeah, and if you still feel that we did not answer your exact question, keep coming back and bugging us. Yeah, with that, I would like to move on to the next speaker, Wei Li from Viavi Solutions, who is going to talk to us about the test, the terminal, the UE terminal that was used for testing. Yeah, I think now already he's a presenter, but you need to start sharing your screen, Wei. Yeah, he's starting.
Hello. Hi, good morning. Can you hear me clearly?
We can hear you and we can see your screen, Wei Li. Thank you very much.
Because now I'm using a mobile network, maybe the signal maybe interrupt. I don't know. So if you can't hear it clearly, just raise question. So good morning, everyone. I'm Wei Li from Viavi Solutions. In our project, Viavi is responsible for UE terminal design and system integration. I mean, at the last stage, the integration was moved to Brunel University due to our company's COVID policy. But we explored this whole integration, and today I'm happy to introduce Viavi's UE design based on our prototype platform testbed. Sorry, I have a problem with I cannot go. My screen is frozen.
Yes, we noticed that.
I can present it and you can tell me to move on if you want.
Yes, please.
Okay, I find your slides.
Yeah, thank you. I think my computer has some problem with Zoom. I cannot while doing presentation I cannot move my cursors.
Okay, I'll present it in a minute. Give me a minute. Can you see the screen?
Yes.
Oh, okay. I'll go. I will. Yeah.
Please go to slide 3. Yeah. I need to rectify this progress. We have three parts. Basically, one is hardware design and the software design, and then the results. If you go to the next page, yeah, this is a hardware architecture for Viavi UE's prototype platform testbed. It consists of a server and the RF front end and NIS USRP. This is a software-defined radio platform. It aims to provide a lightweight 5G physical layer protocol and 5G physical layer feature enhancement and faster algorithm validation. The minimum platform consists of one server with x36 CPUs and one NIS multi-channel USRP, which could provide at least 100 bandwidth over radio frequency between 1 to 5.3 gigahertz with commercial level signal quality. In addition, we also solved several bottleneck issues during our platform enhancement progress, such as massive MIMO calibration for multiple channels and RF impairment calibration and multi-user fast blind detection. And this enhanced features enables the testbed with up to 64 channels with a fully digitized beamforming features. And this brings us advanced 5G massive MIMO features, such as multi-user massive MIMO test and a special time frequency 3D channel emulation, and ultra dense 5G user terminal emulation. In IOR projects, we use a minimum platform configuration, which is a 1 USRP, 1 server, and 2 radio channel configuration. Yeah. And that's an introduction for our hardware architecture.
You want the next slide?
Yeah. So in this slide, I will introduce you our hardware and system for VLC link. Firstly, the base station DRAM, which is a DRAM and RRH generates a 5G signal, and then convert 5G baseband signal, then convert this baseband signal into 15 megahertz, and then feed into a 2-stage amplifier, and then feed into the 4 switch, and then the VLC signal will be generated on a 4 VLC panel in a time multiplexed way and received by the VLC receiver. The radio signal was then generated, converted from the VLC receiver. And the USRP then digitized the radio signal. It treats this radio signal as a normal 5G signal. And the UE server demodulated the 5G signal in a real-time way and hand back to the higher layers. Yeah. Next slide, I will show the millimeter wave link. John, please.
I got it. You should see it. Can you see it?
Yes. Millimeter wave links share the similar connection topology. Base station generates 100 megahertz bandwidth 5G signal and converts the 5G signal into 3.5 gigahertz. Sorry, I made mistakes for the frequency, and that frequency was a previous specified. And then the base station feed the 3.5 gigahertz center frequency into a power adjustment module to amplify the millimeter wave signal into a proper power to be modulated by the millimeter wave transmitter module, and then be received by the millimeter wave receiver. And then we, at the USRP side, we still receive a base radio signal at frequency of 3.5 gigahertz frequency band. And then at the UE side, we still treat the received signal as a normal 5G signal, similar as the VLC, with the difference of bandwidth and resource allocation. And that's a millimeter wave link. Then I will introduce the software part of the UE design. The software architecture mainly consists of 4 parts: user interface, real-time signal processing system, and the RF interface, and the logging engine. The user interface provides a UE to display, a GUI to display signal analysis results such as EVM, Muller, time frequency signal strength. The real-time signal processing system provides lightweight multi-user 5G signal protocol processing capability. And the RF interface drives a 5G radio module based on a 10 gigabit Ethernet high-speed data link. This guarantees our USRP's radio with two-channel full duplex 5G capability. Yeah, that's a software architecture we design. Yeah. Then we have DSP modules to process the 5G signal, both for the downlink. We have the cell surge and cell flow and timing error compensation, and the FFT channel estimation, equalization, and demodulation, and phase compression and derate matching, and the decoding part, both for the control channel and the data channel, which is a very conventional architecture. But we have different, we have developed some advanced techniques to make sure our DSP has a real-time capacity to process 5G signal. And if you go to the next slide. Yeah, because the 5G has a bandwidth of 100 megahertz and up to 8 layers so far, and this requires very high processing power for the platforms. Unlike RunEL's FPGA-based platform, we are using x86 CPUs, which is software-defined. So this requires us our CPU to customize all the signal processing, which is designed for ASIC and FPGAs. So take an example. If we have we configure the system with a 4x4 MIMO and MCS of 27, this requires around 1 million log-like ratio calculation over 500 microseconds. This is very huge. So to meet this requirement, we have done quite a lot of exploring in our testbed prototype platform. First is the system. The system we are now using a low latency kernel, which guarantees all the algorithm modules will be strictly limited in a time frame. And then we also did some tuning for this system, like frequency optimization, interrupt disabling, and the timer scheduler, and huge page, and hyper-threading optimization. And we also have used some advanced technology like Luma and cache alignment. And for the RF part, we also adapted DPDK to drive the USRP to guarantee we can offload the CPU and then let the lead card to do the traffic. We also developed some advanced algorithms to do the signal processing, like for the LR calculation, we adopted max log algorithms to reduce the calculation, but we don't have much sacrifice for the performance. This algorithm is even faster than lookup table. We also have a very fast blind detection algorithms for multi-user scenarios. If we enhance this testbed for the we enhance this IR scenario for the multi-user scenarios. We can have like a 60K users easily with like at most two servers. Yeah, this is a DSP implementation we have done. If you can go to the, yeah, this is a frame structure for VLC link. First, we allocated one symbol for control channel and for the first symbol. Then the second symbol is allocated for the channel estimation and the positioning. In symbol 2 and to symbol 13, we are using these symbols for data, which provides the UE with 10 megahertz bandwidth and 5 megabit per second data rate for current demo. But we already we tested previously. The UE is capable to demodulate visible light up to several tens of megabit per second. We also achieve a position accuracy with below 10 centimeters. And yeah, this is a frame structure for millimeter wave link. At the left side, it shows our current 5G frame structure for millimeter wave link. In this frame structure, we planned 4 UE subsystems. You can see here we have 4 grids for the UEs, for 4 UEs. Each UE will be allocated with 120 RBs. This results around 50 megahertz bandwidth. And the frame structure at the right-hand side will be our new frame structure. This new frame structure allocates each UE with 272 RBs, and results full 100 bandwidth, and give the UE higher data rate. In addition, uplink symbols are introduced for information feedback and the positioning measurement based on a millimeter wave signal. If we go to the next page. So far, we have achieved downlink VLC and uplink VLC working, and VLC downlink VLC for the UE working at 50 megahertz band and the bandwidth of 10 megahertz. And for millimeter wave, we have a center frequency of 3.5 gigahertz and a bandwidth of 50 megahertz. And the data rate for the VLC is 5 megabits per second, and millimeter wave 300 megabit per second. And for EVM performance, we have a VLC signal of 7.2% and millimeter wave 7%. This is average performance, but previously we have done a measurement with good performance, with best performance of like 3.0 and 4.1 respectively for VLC and millimeter wave. Yeah, the next stage is to explore the high-speed link for the millimeter wave. That's the presentation for today. Thank you for your time.
Thank you very much, Wei. I think we have maybe time only for, yeah, there is one question. Okay, let me first read out the answer to one of the previous questions. So the overall power consumption of our VLC design is less than 3.5 watts, considering both communication and illumination or lighting. And then the new question is to you, Wei Li, and but maybe not only to you, is why did you use DMRS for positioning instead of PRS?
Do you mean PTRS or PRS?
PRS.
Because we feel that DMRS is enough, totally enough, and DMRS is already there for each UE. So we don't need to modify the protocol. It's basically the idea is that if we can reuse the current protocol, then we use it.
Thanks. I think if there is still further questions or something to be clarified around that, then we can take it offline. Because thanks, Wei Li. And with that, I would like to move to the last talk in this first block, which is the VLC receiver discussion. And this will be given by Bastien Bechadergue from Oledcomm.
Yes. Hello, everybody.
Excellent. We can see your screen already. I can confirm that.
Can see my screen. That's great. Let me just cut the camera and then I will get started. How about that? Okay, anyways. So you can see my screen and everything's good?
Yes.
Okay, perfect. So then, good morning, everybody. My name is Bastien Bechadergue. I'm in charge of the research activities at Oledcomm, which is a French startup developing light communication solutions. And I am now going to talk to you about the visible light communication receiver that we designed for the IoRL project. So first, I will detail the main design constraints and objectives. Then I will present the architecture of the VLC receiver design, as well as its performance, before concluding with the main results and the future works. Now, as you can imagine, the role of the VLC receiver is to receive the visible light signal. So its design is obviously constrained by the properties of the transmitted signal. This transmitted signal is theoretically an OFDM signal with a subcarrier spread over a fixed channel of 10 megahertz bandwidth and ranging from 10 to 20 megahertz. So this means the receiver must have a flat electrical bandwidth at least between 10 and 20 megahertz. Now, this data signal is sensed by a non-ideal white light source, which has its own characteristics. First of all, this light source has a specific electrical modulation bandwidth, here represented on the left, which will induce some distortions in the transmitted signal, and that the receiver must take into account. And then the light source also has a specific optical spectrum, represented by the yellow curve on the right, which has a large component in the blue region and then large components in the yellow and red regions. So in the end, this means that our VLC receiver must be sensitive to these wavelengths as well. Now, after emission by this white light source, the data signal propagates through free space before reaching the VLC receiver. And in order to estimate the communication performance, a common metric is obviously the signal to noise ratio, the SNR, which is the ratio of the received signal power with the receiver noise power. And the received signal power obviously depends on the transmitted signal power, but also on a lot of other parameters, which you can see on the second equation here. I will not go through all the parameters, but I would simply say that the received signal power is affected by three main kinds of parameters, which are the light source parameters, the link geometry, which is represented on the right, and the receiver parameters. And here we are logically interested in the receiver parameters, which influence this signal power. And these parameters are the photosensitivity, the sensitive area, and the optical gain. The photosensitivity defines the capacity of the receiver to turn photons into a current. So basically, the higher the better. Also, we want this sensitivity to be as high as possible in the visible range of wavelengths. Then, ideally, the larger the sensitive area, the better. But a large sensitive area means also a larger internal capacitance, which means reduced bandwidth. So we want our photoreceiver to have a large sensitive area, but not too large so that its bandwidth remains sufficient. And finally, increasing the optical gain allows to increase the optical power, but increasing this gain also reduces the receiver field of view, and reduced field of view means lower coverage. So there's also a compromise to be found on the optical gain. Now, with that in mind, the existing photoreceivers in this table, some of these receivers are listed and classified according to their sensitivity, sensitive area, and bandwidth. And as you can see, most of them do not have satisfying values for these three parameters at the same time. Actually, only the last Hamamatsu receiver meets all the criteria, so we decided to define this receiver as a reference receiver. Now, in more detail, this photoreceiver has a rather large sensitive area of 7 square millimeters with an electrical bandwidth of 40 megahertz and a photosensitivity that, as you can see on the bottom right corner, is optimized for visible light and reaches at most 12 amps per watt. Such a high sensitivity is actually only possible because an avalanche photodiode is used in this receiver. But as a comparison, most standard pin photodiodes, which is the other main photoreceiver technology, have a sensitivity lower than 0.7 amps per watt, but also similar sensitive areas. So our conclusion is that this Hamamatsu receiver is actually, technically speaking, more or less the best receiver we could find or design for the IRL application. However, this receiver is also rather bulky and expensive, and avalanche photodiodes are rather complex to use and to, let's say, use in industrialized products because they need a rather large bias voltage. So what we tried to do, given that we already have this reference receiver, was to design a simple, cheap and compact custom photoreceiver using pin photodiodes that would compete with this reference receiver. So how was this custom receiver designed? First, we made a link budget analysis to theoretically estimate the optical power received according to the receiver position and orientation. Now, this is a very usual design step, but we actually noticed that the link model, which is commonly used, assumes the light sources are point sources, whereas in our case, the light sources is a circular spot. So we eventually proposed a new model, which is more accurate for these kinds of light sources, and which was actually published in a journal paper. And then we carried out the link budget analysis with this model. From this preliminary link budget analysis, we determined the general architecture of the VLC receiver, which is represented here and includes first an optical module to increase the light flux collected by the photodiode, then the pin photodiode to convert this light flux into a photocurrent, then as a transimpedance amplifier to turn this photocurrent into a voltage signal, and finally some post-equalization, amplification, and filtering stages to extend the receiver bandwidth and clean the received signal. Now, about the pin photodiode, which is probably the most vital component in this chain, we made a comparison of the existing components, and we eventually picked the photodiode, which shows the best trade-off between sensitive area, sensitivity, and bandwidth. And you can see these parameters in this table, and you will notice that the sensitive area is more than 4 times larger than that of the Hamamatsu receiver, but that the photosensitivity is indeed almost 20 times lower. Then obviously we designed the electric board, embedding the transimpedance amplifier, the post-equalizer, the amplifiers, and filters. And you can see 2 of these boards in this picture. You will notice that each one actually has 4 photodiodes, simply to increase the sensitive area and compensate for the low pin sensitivity. These boards also have an SMA interface for connection with the baseband and the USB interface for power supply. And additionally, they have an infrared LED that was integrated for test purpose. So in the end, these receivers have a pretty compact form factor with a diameter of 48 millimeters and a thickness of 6 millimeters, and also a rather limited price of around 50 euro compared to several hundreds of euros for the Hamamatsu receiver. Now, once we got these receivers, we logically made a first round of validation tests. First, we evaluated the performance of the reference receiver, the reference Hamamatsu receiver, in an IRL-like scenario. So a 5G NR signal was generating using a server for the higher layers and the USRP for the lower PHY layers. And this USRP was connected to the light transmitter, represented on the top right corner, which was sending data to the VLC receiver. And then the uplink from the VLC receiver back to the USRP was made with a wired connection. And using a computer, we could monitor the communication metrics, such as the EVM or the data rate. Note, and it's important, that this setup was used only for intermediate tests, and the final test results will be actually presented later today, and they have been obtained using an actual remote radio like that. So using this intermediate setup, we first calibrated some transmitter parameters to mean that the USRP gain value that would better match the transmitter properties was -3 dBm, in which case we could get an EVM of 3.75%. That was sufficient to transmit 64 QAM. Then we also checked the impact of the transmitted bandwidth and noticed that increasing this bandwidth actually degrades the performance, the EVM performance. But however, with the 10 megahertz bandwidth, we could still get an EVM of around 5%. Then we tested the EVM performance against the communication range and also the type of channel, and we found that the maximum communication distance was 1.8 meters with a 5.82% EVM, enabling 64 QAM signal reception. And in parallel, we found that the optimal EVM is logically obtained when the transmitter and receiver are aligned and allows a maximum data rate of around 31 megabit per second. Again, these are intermediate tests. Finally, we found that the link remains robust to transmitter and receiver rotations. As for example, with the receiver rotation of 45 degrees, the EVM is still lower than 7%, which enables 64 QAM signal reception. Then we checked the performance of, this time, the custom-made receiver, the pin photodiode-based receiver, starting with the evaluation of the modulation bandwidth. On the receiver side, we found that the 3 dB bandwidth is actually, as represented on the left, 38 megahertz with a 0.5 dB gain variation between 10 and 20 megahertz. We also checked the 3 dB bandwidth of the infrared LED transmitter, and we found, as represented on the right, that this bandwidth was around 20 megahertz with a 1.5 dB gain variation between 10 and 20 megahertz. So once we knew that the transmitter and the receiver bandwidth of our system were okay, we moved to data rate and coverage tests in order to evaluate the best performance achievable with the design receiver. But we actually faced two problems at that time. We didn't have any white light sources available at Oledcomm, and we didn't have either the modified 5G NR MAC and FINE designed by the IoRL partners. So instead, we used a custom-made baseband based on the g.VLC standard for light communication, which has been published by the ITU in 2019. And we use the infrared LED transmitter, the infrared LED as transmitter, because we knew from the previous test it had indeed enough bandwidth. So on the left, you can see the transceiver board previously shown, connected to, at the bottom, a baseband board embedding the g.VLC MAC and FINE. This system was then integrated into a mechanical enclosure, shown on the right, and including an infrared optical filter to reduce the effects of ambient lighting. Then an access point was installed on the ceiling, and the user device was connected to a computer with a vertical distance of 2 meters between both devices, as represented in this photo. And then the computer was used to monitor the communication metrics, such as data rate, the SNR, noise level, and the user devices was moved in the reception plane in order to establish a data rate versus coverage map. This map is represented here, and as you can see, the maximum data rate we obtained was 100 megabit per second, whereas the maximum coverage was 11 square meters. Now, the data rate does actually not remain constant over this coverage, but it decreases as the receiver moves away from the axis of transmission of the access point. So in the end, we observed that the data rate remained larger than 90 megabit per second over 2.5 square meters, larger than 75 megabit per second over 5 square meters, and larger than 50 megabit per second over 10 square meters. Now, to conclude this presentation and to summarize it, I can say that Oledcomm has designed a rather cheap and compact with the receiver module, adapted to light communication over channels of at least 20 megahertz bandwidth, that the maximum data rate with this receiver is 100 megabits per second, whereas the maximum coverage is 11 square meters. But however, as you probably noticed, this receiver has not yet been tested with the IRL system and its white LED. So this test will actually be performed in the coming weeks, along with tests of the IRL system with an infrared emitter rather than the white LED, so that we can then compare the respective performance of both setups. Thanks for your attention, and please feel free to ask any question you may have now or even later at this email address.